This is a presentation for the Autocomplete project. My name is Mayao and I'm from section AB. For deliverable 2, we're doing BST code tracing. The first step is to add all terms into the array list. The insertion order is not in dictionary order, but after we call testing.addAll, call collection.sort using this rule. So this graphic would be the accurate representation. Everything is sorted. And for all matches, I'll go to IntelliJ and code trace line by line. So let's go ahead and step into all matches. We'll first create a new array list called results so that we can return at the end. And then we check if the prefix is invalid, so either the prefix is null or it has a length of 0. In this case, the prefix is do, so we skip that. Then we find the start index using collection.binary search. So we skip all the prior terms and we will start checking from do. The while loop condition is while the starting index is smaller than the array list size, we'll extract the first term using the starting index that we get from binary search. So that will be do. And then we'll use isPrefixOf method to check if the term is a matching term. So in this case, do matches the do prefix. We'll go ahead and add it to the result. And then since the starting index is 4 is smaller than 7, we'll continue the while loop. We extract the second term, which is doggy in this case, and we pass in isPrefixOf again. And because doggy has the prefix of do, we add it to the results array. And we increment the starting index. Since 5 is still smaller than 7, we will extract the next term on index 5. Since dog is a matching term, we will also add it to the result array. Finally, we know when to stop when the term no longer has the prefix. So in this case, the term pilot doesn't have the prefix of do. So we will return the result immediately because we know the list is sorted in a way that all the matching terms are in consecutive order. So if we're at the place where there's no matching term, then that guarantees that all of the terms after that are not matching term. Finally, for the assertions, the expected and actual share the same size because there are 3 terms that have the do prefix, which is do, dodgy, and dog. We manually constructed the expected array so that we can test if the actual results have all the matching prefix. Why this expected contains all of the same terms as actual, I interpret it as how do we avoid adding the wrong terms into the actual array. The reason being the BST search will find the index of the first matching term using binary search. So if it's alpha and cats, they will be ignored. And then from do, which is the first matching term, the traversal would only explore terms in the sorted order. It will stop immediately when a term no longer matches, which is pilots. It doesn't have the prefix. This guarantees that no invalid or actual terms are added to the results. Then finally, why does actual contains all of the same terms as expected? In other words, how do we not miss any of the terms? Because the array is sorted in dictionary order, all the valid terms with the same prefix are there next to each other. That guarantees that no expected terms are skipped. For deliverable 3, we're doing the TSD code trace. The first step is the add-all diagram. We construct this tree from this insertion order. So we do alpha first, and then we do delta because we don't include A, so we go the other way. And then we insert cats because C is less than D. And then we do doggy. We don't include D, so we go down, but O is greater than E. We don't include E, so we go right. We do doggy. And then we do pilot. We don't include D, and P is greater than D. We go down. Finally, for the dog, we don't include D, so we go down. We don't include E, so we go right. We don't include the D, so we go left. And finally, we store the dog. And we'll go to IntelliJ to trace through the all matches method. To code trace the all matches, we'll first check if the prefix is valid. In this case, prefix is not null. Then we'll create a list called matches to collect all the matching terms. We use the get methods to know where to begin searching. It will find the last character. So if it's DO, it will find the node of storing the O and then return as the root. And if we expand this, you can see it's storing the O. The is term is true because DO is a term. And we just keep expanding the middle nodes. And you can see it's DODGY, dodgy. And if we expand the right node, you'll see it has G, so it's DOG. So if the is term is true, we will add it to our match array to return. So initially this size is 0, but after running this, we'll see the size is 1. And if we go to JGrasp, you'll see the DO is stored in the return array. We collect terms into actual by doing these recursive calls. We will continue to check if the root is null. It will collect the left, middle, and right branches. Every time we go down a level, we will append that character to the prefix until we see that the root, the is term field is true. To ensure we are exploring other versions, after dodgy, we will delete the characters after each recursive call. So dodgy will become DO again, so we're not carrying those extra prefix. We know when to stop collecting the term when the root is null. It will give us null because there's no more characters, and that is when we return the list. Finally, for the assertions, again, the expected and actual share the same size because there are 3 terms do, dodgy, and dog have the do prefix. How do we avoid adding the wrong term? My get methods will navigate to the exact node corresponding to the last character of the prefix. So in this case, O in the prefix of do. So if we go back to this diagram, my get method would navigate to here. So at this state, the prefix is do, and then my collect method would only recursively explore this subtree. So we will not touch any of the other trees that has wrong terms or invalid terms. Then how do we not miss anything? My collect method will perform a full recursive traversal of the left, middle, and right children of the prefix node, so that ensures that every term in the TST, starting with the given prefix, is visited and added to the result. For sequential search, the big theta bond would be theta of constant. The array list.addAll will append a constant amount of new terms into the array. Our assumption is that there are no shifting or resizing involved, so the runtime is not dependent on the prior data. And for all matches, the worst case would be theta of n, because since we are not sorting the array, the matching term might appear at any places, so the algorithm needs to examine every stored items term by term to check if the prefix is what we're looking for. For binary search, the worst case for the add-all would be theta of n log n. We're inserting constant terms into the dataset, and then we will sort the entire list using collection.sort, which use tim sorts in Java, and it guarantees n log n in worst case. For all matches, the worst case is theta of n. This is when all the n terms in the existing datasets share the prefix that we're looking for. Binary search has log n, but if all the n terms share the prefix, the collect will visit all of them, so there will be n iterations. And n dominates log n, the worst case will be theta of n. For TST, both the add-all and all matches will have worst case theta of n. This is when the tree is really spindly and looks like a linked list. So we need to traverse all the way to the bottom to insert the constant terms, and we also need to traverse down to the bottom to find the matching terms. Finally, for TreeSets, the worst case for add-all will be theta of log n. It will trigger the maximum number of rebalancing operations, but since they're constant, it's negligible in asymptotic analysis. And each insertion into the red-black tree is theta of log n. For all matches, the worst case would be theta of n. For tail sets, it visits every matching terms. So if we have n matching terms, it will take theta of n. If we add them together, n would dominate the log n. For experimental plots, the fastest implementation is sequential search because it doesn't require any sorting. We're just adding the constant term to the back. The drawbacks of tree data structure is that the insertion runtime can be pretty costly. For all matches, the slowest implementation is also sequential. Because we didn't sort the list, we need to examine every term, and it's dependent on the dataset size. The benefit of tree is that since we take the time to sort the data, we can quickly find which subtree to explore, and we can ignore most of the unmatched terms. There are some disagreements between the experimental and asymptotics. For example, for binary search, we hypothesized that the worst case would be theta of n, but in real life, it's log and almost constant. That is because the worst case we hypothesize is when all the n terms in the dataset share the same prefix. For example, every city name starts with an A and the prefix is A. So add-all would insert the new terms into a really spindly tree, which requires n traversal. All matches also have to scan all the n terms in binary search and in TST tree sets. In average cases, however, most prefix matches only a few terms. The add-all would insert node without having to traverse the entire tree. The all matches will find the starting index or the prefix node and iterate only a small portion of the term. For asymptotic setup, we assume that there's already a tree with n terms exists. But for experimental, we construct an empty instance and rebuild the trees from ground up. So this is the code snippet. It's reassigning it to null and then add all the datasets. So that causes the tree sets to not have a log n, but n log n runtime for add-all. Finally, for asymptotic, we assume that we're adding constant number of terms to the datasets. But in experimental, we're adding n numbers of terms to the datasets.